This video is called Extensions, and it is a brief introduction to how you secure that long data sets are treated adequately by adding missing lines in the sheets for individual vials and new variables, how to make them and how to make them in all your sheets. The first example I will use is a leakage test that was conducted recently by Lars Molstad, where we had a very large data set, very many measurements in each vial, and we need to extend the number of lines in the sheet, and I will show you how to do that. Started looking at the raw data, you see that there is a large number of measurements here down to line 94 in the raw data for N2, and now if I go into the default version of Kincalc to an individual sheet like sheet number 1, you see that it doesn't reach further than line 100. In N2 it goes down to line 94, but it starts at 1, so in this case we have 92 measurements, whereas in the sheet here for number 1 it goes only to 74. Now, in order to include the remaining measurement for the sheet to pick up the raw data from that, I need to mark the line. I can do it this way, or I can mark it on the left, very left column, but I do it this way just to illustrate what I'm doing. And I copy that and paste it down. And now you will see that the sheet for vial number 1 is now picking up all the data and then adding a few blank lines which we can delete because we don't need them. Now the next thing you want to do is, or actually you will do this from the very beginning, but I'm just illustrating it with one sheet first. But you want this to apply to all the sheets, because you can see that the individual sheets have only 74 lines. It starts at 26, ends at line 100. So we want to do this to all the lines. In this particular experiment I have only 11 vials, so I don't have to bother about the rest, but I want to do this to happen for all the vials. I can do it manually in each sheet, but it's more efficient if I do use a trick where I open number 2 in this case, because I've already done the thing in vial number 1, and then I scroll over to, let's say I include number 12. I hold down the shift key and left click on 12, and now I have activated all my sheets. So what I do now on the screen will happen in all the sheets. So I take this line, copy it and paste it down, and you can go out by clicking on 1, and now you can inspect number 2, and you see that it's been pasted down in number 2, number 3 and 4, etc. So this is a trick to make changes to individual vials. You will also see that the master lacks more lines than to line number 100, so I will have to do the same extension here. Make sure that you get all. Copy this one and paste it down. That's enough. So now I have a sheet which is extracting all the data from my experiment in all the sheets of relevance. The next thing I want to show you is how to make a derived variable and to make it for all the sheets. So let's say in this particular case I'm interested in quantifying the leakage So in order to calculate that, I put 0 leakage of oxygen and nitrogen in my parameter set, and that means that the estimated rate of N2 production, apparent N2 production, is my leak rate, and the same is true for oxygen, the rate, although oxygen is calculated as a negative rate. But we can concentrate on N2. And let's say that I wanted to calculate the leakage for each injection based on the or per hour based on the volume, expressed in volumes rather than moles. So in that case, I need a number, and that is the mole volume of the gases, which is the inverse of the parameter set here. And I have to make sure that I have the right temperature, because you will see that this number changes with temperature. So if I write 10 degrees here, you will see that this number changes. But I was running this experiment at 20 degrees, so 20 degrees is the right value. So I want to express my leakage as nanoliters of N2. Okay, I have the rate here in column AP. So I go to the right, find an empty space, and that is the rate per hour. So I write here, first of all, I pick up, I calculate a constant, which is 1 divided by the, I'm doing this a little bit clumsy just to illustrate what I do. This is the mole per liter gas, and the inverse of that one is the volume per mole. So this is actually liter per mole, right? So that's a constant that I will use. Now I take this one, put equal here, and I can scroll over here to show you exactly what cell I take. It's the rate. Here I have the rate, one particular rate in moles per hour. But what I want to have here is the nanoliter N2 per injection minus 1, and in order to calculate that, I have to have the rate per hour here, and I multiply it by the same time span that I calculated the rate for, and then I have to, and that is in mole N2 now. In order to get it in nanomole, I multiply it with 1 E9, and then I multiply it with the number of nanoliters per nanomole, which is my constant up here. So I click on that one, B20, and if I now press down F4, you will see that it dollared BX20, and that means that is a fixed star. When I propagate this down, I get a column of numbers. I can skip the last one. It looks, I want to format these cells to numbers. And let's format this as well. So this is now my a new variable. It's nanoliter of N2 per injection. And if I now make this is injection number 2, and I make a new line here, is equal to this one plus 1, so I have the number of injections, and then I can make a graph showing the leak rate in nanoliters of N2 and per injection, and the net injection numbers are here. It's noisy, but it is something between 500 and 1,000, and the average is 700. Now, if I want to propagate this to the other sheets, I can do this with the same trick as I showed you for the extension of the individual sheets. And I will show this for sheet number 1 first, and then see how we do it for all of them. So I take this column down, copy it, and I remember that it is going to be pasted into BW20. Then I go to sheet number 1, I go to BW20 and paste it, and there I have the same column. Now if I want to do this in all the sheets, I can copy this one again and then do the same thing. I go to number 2 and then scroll over to 12, hold shift key down so I activate all of them, and I can move up to BW20 here, and I paste it. Now I have the rate of leakage in each vial in each of the sheets, and if I go out you will see that I find the same column in all of them. So this would be my variable that I want to inspect for all the sheets, and in order to do that I use another part of Kincalc which is very useful, and that's called crosscuts. Remember that my variable that I want to look at is in column BX. If I now go to crosscuts, you will see that it is lining up all the vial or flasks number 1, 2, 3. There is a formula in here which secures that it extracts the data from the individual sheets depending on what I write in cell D11, the column. So I was interested in BX, and now all of a sudden we have the leakage of N2 in nanoliter N2 per injection for the individual vials. But you will also see that the crosscut spreadsheet hasn't extracted all my data because it stops at 35 hours. So in order to extend it to include all my measurements, I just take this line here, copy it, and extend it down. And then until I come to the end. So that's how you secure that you see everything in the spreadsheet. These are old figures that we don't need to bother about. So now I have all my leakages, and I can inspect them one by one by starting at the first one, the first zero is meaningless, so I can extend it to like that, and insert an XY graph, and it looks like it's keeping a stable level throughout the many injections. Now this particular experiment, Lars programmed the robot to pierce the septum 10 times between each gas sampling. So there's actually an astronomical number of piercings here, which hasn't resulted in leakage in this bottle, because this bottle contained 100 microliters of oxygen. Now you can see what happens if we take a vial where there was no water at all in the vial. The leakage was low to begin with, just as the other, and then it escalates towards the end. But mind you, this means that the septum at this stage here has been pierced. Let's say we can calculate that, because here we have 10 piercings, and this one is 10 plus 11, including the one with the sampling. So that would actually be like that. So 1,000 piercings. So that septum has been pierced 1,000 times when we have reached the end of the experiment. So we can make a new graph, or we can just modify this one and say that this is my x value, and this is my title, leakage, nanoliter N2 per injection -1, and my x-axis, I add an element to the axis, primary horizontal, number of piercing. Okay, and I can make this look a little bit nicer. Format the axis to have. Let's just show you a little bit about the how you make nice graphics. So it escalates. In the case where I have a dry vial, it escalates towards the end, but that's after 800 piercings, so it's quite robust. But even then, even after such high numbers of piercings, if I have a little bit of water in the vial, the leakage is effectively eliminated. And this is a very new experience we have with the robot. But I use the example to show you how you make derived variables. We constructed the variable in the individual sheets, and then we looked at the variable efficiently throughout all the treatments in crosscuts. This is one with water again, water again, and water again, and then we have one dry vial which is then showing the same escalated leakage towards the end. Now, in order to compare them, we can extend this one by making a new graph. No, it's not easy to extend it, but you can make a new one where we include two of them. In one graph. And then in order to see the entire scale, we can change this to logarithmic values. And you see that the dry vial having higher leaks throughout and escalating leaks towards the end. So this shows you how you robustly can scan through a whole set of experiments. Oops, sorry. I regret that change. So you can how you have all the data together. And of course you can make average values, etc., etc.